SecureCPS is a joint research program by Global Infotech, Embry-Riddle Aeronautical University, and Vanderbilt University, focused on securing cyber-physical systems. The initial focus of this research is the Arapaima nanosatellite mission.
7, 6, 5, 4, 3. And the RS-68A engines roar to life and liftoff of the United Launch Alliance Delta IV Heavy carrying the NRO.
Arapaima is an Air Force University nanosatellite program currently in the design phase. The Arapaima mission will conduct proximity operations near a resident space object, also called an RSO. The launch of the Arapaima nanosatellite is planned as a secondary payload aboard a Delta IV Heavy. A few orbits after deployment of the primary payload, the Delta IV upper stage will eject Arapaima from its launch canister. Then, approximately 45 minutes after ejection, Arapaima will power and boot its primary computer system. Once the power-up and boot-up sequences are complete, Mission Control establishes contact with Arapaima and performs early orbit operations, during which all nanosatellite systems are tested. At the successful completion of checkout, Arapaima is commanded to use its propulsion system to approach the RSO. For the first Arapaima mission, the RSO will be an empty upper stage or a defunct satellite. Proximity operations are required to allow the Arapaima nanosatellite to build a visual and infrared textured 3D model as it orbits the RSO from a distance of a few kilometers. At the current operational altitude, one orbit around the RSO requires approximately 90 minutes. To accomplish this mission, Arapaima must perform on-board processing of the images it has acquired of the RSO and, due to bandwidth constraints, transmit only selected data to Mission Control. This animation illustrates the Arapaima orbit, but has been sped up and scaled for illustration purposes. Visible, infrared, and laser imaging data from Arapaima's sensors are transmitted to Mission Control for analysis and archival. A key feature of Arapaima development is that the nanosatellite and its support systems are completely designed by students. To keep development costs low, Arapaima makes extensive use of commonly available commercial and open-source hardware and software. Because of the open nature of commercial and open-source systems, the same hardware and software is available for anyone to examine, including individuals with malicious intentions. As a result, malicious code could be added to software or hardware. Clever and surreptitious techniques can be used to trigger malicious software once the nanosatellite is in orbit. In one attack scenario studied by our research, a quick response code, or QRC, was attached to the RSO. The QRC triggers malware within the Arapaima computer. This malware was added to the Arapaima software somewhere within the supply chain. Despite careful testing at Embry-Riddle Aeronautical University, the trigger event might be complex and the malicious code might not be detected. The satellite could be launched with high expectations for success. Once deployed, as Arapaima approaches the RSO, its sensors see a triggering image, which then activates the undetected malware. Now the malware goes to work and seizes control of the space-ground radio link. Thus blocking access by Arapaima ground control. Arapaima begins its communication with the malicious ground control. This leaves Arapaima under the control of the malicious party. SecureCPS defeats this attack using three key components. These components are the root of trust, GAMAS, and anomaly detection by machine learning, or ADML. The root of trust is a cost-effective, complete chain of custody device contained within a small, simple, verified hardware component providing the basis for trust that is extended throughout the Arapaima nanosatellite architecture by GAMAS. The root of trust assumes any nanosatellite subsystem could be compromised. The root of trust is the only trusted subsystem from which GAMAS verifies its own execution and it extends trust throughout the SecureCPS architecture. The root of trust then becomes the basis for 1. Check the checker. The root of trust ensures that GAMAS is a known good binary and periodically checks the operation of GAMAS to ensure it is not subsequently compromised. 2. Binary signatures. The root of trust provides known good signed binary signatures to GAMAS. These signatures are used by GAMAS to allow good, in other words, whitelisted, binaries to run, and prevent the execution of all other binaries. For enterprise applications, GAMAS has the ability to use whitelists, blacklists, and a third unknown list. GAMAS is low-level software that extends trust throughout the nanosatellite architecture. GAMAS ensures all programs running on all nanosatellite computers are authorized and have not been altered by comparing signed hashes of the binary to the hash provided by the root of trust. If a program's hash, demonstrated with an enterprise application called malware.exe, execute, it is terminated. For Arapaima, if the executables are not identical to the hash stored in the root of trust, or a program attempts to run in a mode where it is not expected, GAMAS prevents program execution before it begins. GAMAS also provides kernel-level instrumentation of all Linux real-time OS API use, thus providing much of the data needed by the ADML subsystem. Unlike a general-purpose computer, a cyber-physical system is far more predictable, especially within a specific mode. During our research, we exploited this property of cyber-physical systems to apply machine learning to build mode-specific models that detect anomalous behavior with enhanced accuracy. This animation provides a simple illustration of how one such model would be built. During ground testing, the number of propulsion pulses per second is counted in 3 axes. As shown by the yellow cone, these test samples define the boundary of what is normal. If propulsion behaviors fall outside what was observed during ground testing, this behavior is flagged as abnormal. Now Arapaima is protected by SecureCPS, and the effect of the malware is far different. When Arapaima sees the QRC trigger, the malware attempts to run. However, SecureCPS detects this malware is not on the authorized list for this mode. In addition, SecureCPS sends an alert to Arapaima ground control. This alert identifies the specific binary that attempts to run, so further analysis can be performed by the Arapaima ground team. Arapaima is restored to normal operations and the attempted takeover is easily avoided. Our research reveals that the GAMAS and ADML, rooted in an uncompromisable root of trust hardware component, provide a cost-effective, highly secure approach for imparting cyber-physical security to a variety of important mission systems. While our research has focused on the Arapaima nanosatellite, SecureCPS will help secure cyber-physical systems found throughout our nation's critical infrastructure and transportation systems.